This is a painting by Claude-Joseph Vernet. It shows road building in France in the 18th century, when all work was still carried out by hand. There's a group of engineers in the middle on horses, and the foreman is giving a report about the worksite in a servile manner. 250 years later, we have the age of compact asphalt technology. With Dynapac equipment, two types of asphalt mixes can be paved at the same time with a performance of 1,100 tons of material an hour. Dynapac compact asphalt technology is the answer to your needs when it comes to cutting construction time, improved quality and economic benefits. What is the current traffic situation? A continuous increase in traffic volume, a rise in axle load, a rise in heavy goods traffic. The road becomes the warehouse, and the consequence, more and more traffic jams with significant disadvantages for road courses. In contrast to this, we've planned the lifetime of road courses. Wearing courses, 10 to 15 years. Binder courses, 15 to 25 years. Base course, 40 to 50 years. And roadbed, 50 to 100 years. Usually you'd have to replace the wearing course twice in 25 years. With compact asphalt technology, we can prolong this lifetime to the lifetime of the binder course, and this is very economical. Have a look at some current problems. Roads become greasy, problems with evenness, problems with grip, problems with deformation resistance, potholes. And there are also problems with interlocking between the courses. The cost of repairing our transport network has reached gigantic proportions, with public funding hardly able to cover this cost. Economic future prospects. Depending on the ability of traffic systems and the power of the mobile economy to compete, there is no end to traffic growth in sight. The road is by far the main means of transport. In Germany, 70% of goods are transported by road, and traffic jams are an increasing burden for the community. The budget can only be maintained in the medium term by improving quality. The aim, a long lifetime combined with minimum maintenance. And quality can only be achieved when you strive for homogeneity consistently. Compaction efficiency is greatly influenced by the temperature of the asphalt mix. The following animation shows degree of compaction as a function of the number of hits from a Marshall hammer. The red line indicates the theoretical degree of compaction achieved at 150 degrees Celsius. 100 hits results in a degree of compaction of over 101%. The following two lines indicate how sensitive the asphalt mix is to temperature during compaction. To reach a degree of compaction of 98%, 100 hits at 120 degrees is required. You'd need the full fault energy to get the same result. If the temperature falls to 100 degrees or below, even full fault energy isn't enough to compact the asphalt on 97%. The void content is almost 8%. This is normally the case in the cold season. That's why there are problems with the compaction degree, the void content, and the interlocking of the courses. We know the results very well. Short lifetimes. Let's take a look at how a conventional road is constructed, with its separate layers depending on use. And in comparison, the compact asphalt. The cooling of the thin wearing course is slowed down because it's laid onto a hot binder course. Therefore, a longer period of time is available to reach optimum compaction. The high compaction achieved also results in high deformation resistance due to the tightly set grain structure between the two top layers. Here the binder layer is colored green and the wearing course red. You can see the extensive linking and covering. According to the Technical University at Darmstadt, the result is 37 kilonewtons cut power. This is an increase of about 50%. To better clarify the demonstration, we've placed aluminium foil between the two layers. Let's move on to the distribution process. The following animation shows how the asphalt is laid with our new compact asphalt paver and feeder. Firstly, the feeder machine fills the binder hopper. Here the binder's colored green. Then the feeder changes its position and transports the wearing course material to the upper hopper on the paver and fills it. This material is colored red. Now the top two asphalt layers can be laid in one work process, continuously, hot on hot. Let's have a look now at how the compact asphalt machine is built. Here we can see how the first module, a binder container expanded to 45 tons, is connected to the carrying basic unit, the F300 CS paver. The binder container is a self-supporting design. The paver is then connected to the second module, the AM300, which consists of a second storage container with a capacity of 25 tons for the wearing course material, two feeder augers, chute and the second screed. To connect the AM300, the paver drives backwards into this module and locks it in. The design of the compact asphalt makes it easy to transport from one site to another. Let's see how the compact asphalt works in practice, together with the mobile feeder, the MF300C. We're looking here at a country road in northern Germany. The working width is 6 meters. A binder material, 022S with a thickness of 10 centimeters, and a wearing course material, SMA 011S, with a thickness of 2 centimeters, both with a polymer-modified bitumen, are being processed. The green lamp on the mobile feeder signals that binder material is needed in the binder container, which is almost twice the size of the wearing course container. This is due to the thickness of the binder layer. The lorry with binder material docks and empties its asphalt mix into the feeder hopper. The conveyor belt of the feeder transports the material into the binder container of the compact asphalt. With the Dynapac feeder, 27 tons of material can be carried in a paver hopper in 35 seconds, a very good performance and a necessary guarantee for continuous paving. The binder material is laid with the first high compaction screed. The screed used here is a proven serial component. With a thickness of 10 centimeters and 2 centimeters, the light normally switches to red after the fifth binder has been filled. The wearing course mix is now required. The mobile feeder pauses briefly, raises its conveyor to the upper position as the paver continues forward. After a short cleaning period, about 20 seconds, the feeder is in position and the wearing course material fills the upper container. The hopper augers feed the distributing chutes with wearing course mix, which is then conveyed to the second screed. The wearing course mix is then pre-compacted on the hot binder layer, hot on hot. This guarantees the best possible interlocking and bonding of the layer. In contrast to the conventional method in which the wearing course is paved on a cold base layer, the hot asphalt course used here increases the compacting time for the subsequent rolling process. Roads on which the compact asphalt construction method has been used will certainly meet the transport demands of today and tomorrow. These roads will be distinguished by their extreme wearing stability and even surfaces. Compact asphalt can be laid without problem even in the cooler months of the year, thanks to the residual heat in the asphalt binder. Using compact asphalt with a 10 cm binder and 2 cm wearing course can extend the time available for compaction by as much as 5 times. A 50-degree loss of temperature in 90 minutes, a 30-degree loss of temperature in 30 minutes is still always a very good result. Thin asphalt layers such as 4 cm SMA lose heat very rapidly, resulting in a very limited time available for compaction, 70 degrees in 27 minutes. Small rollers are used directly behind the paver for initial compaction of the compact asphalt. They're used only in static mode in order to stabilize the thick asphalt layer before vibratory compaction. Turning the roller before changing direction behind the paver improves the surface evenness. Heavier vibratory rollers follow the small ones to achieve the required compaction. To achieve the initial friction on the stone mastic asphalt constructed here, stone chippings are rolled into the surface with the last rolling cycle. The main advantages of this process are the resulting quality and deformation resistance of the constructed carriageway and the extremely short construction period required. The result is a deformation-resistant road surface without ruts or cracks. Here are some impressions from different work sites and surfaces after compaction. The main advantages of compact asphalt technology are longer life cycle, standard paver attachable modular units, construction time halved, higher quality, and increased economic benefits.